Log on, tune in, find out. Another good idea from Cambridge.
The last generalised talk of the day will be followed by a very interesting discussion session based on what's already been said. So Charles is going to talk to us about EDD. I'm not even going to pronounce that. Generalised geometry and 11-dimensional supergravity, which is work by the Imperial Group.
Okay, good afternoon, everyone. First, I would like to thank the organisers for the kind invitation. So I'm going to talk to you about some work I've been doing with my supervisor Dan Waldron and also Andre Coimbra on EDD cross R plus generalised geometry and 11-dimensional supergravity. The plan of my talk is as follows. First, I'll talk a little bit about what we mean by the internal sector of 11D supergravity, because we're only considering a kind of a restricted dimensional setup of it, and so I'll just briefly review exactly the details of what we mean by that. And this is the theory that we will eventually want to describe geometrically using generalised geometry. In the next section, I'll describe the details of exactly what we mean by EDD cross R plus generalised geometry in this context. Here we're discussing the generalised geometry in the sense of the program originally started by Hitchin and Galtieri. So we have no extra coordinates on the manifold. We just take the usual d-dimensional manifold and we consider the geometry of an enlarged tangent bundle on that manifold. And in this section, we think of this as being like Riemannian geometry, or rather ordinary differential geometry, before we introduce metric. So we can define kind of familiar objects without needing a metric, like Lie derivatives and that kind of thing. In the next part, I'll introduce a generalised metric, much similar to what Hadi was talking about in the previous talk. This will reduce the structure group from EDD cross R plus to HD, where HD is a subgroup I'll define. And this is much like when we introduce a metric in Riemannian geometry. We reduce the structure group from being just GLD to being SOD, the stabilizer of the metric. So here the analog of SOD is HD. And studying natural things that we can do with this additional structure on the manifold, we discover that we can recover all of the supergravity equations in a natural way. But the way that we do this is kind of abstract in this section, so to be a bit more concrete, in the next section I will go through the example of 7 dimensions where HD is SU8 and write some equations with SU8 indices, so you can see it a bit more concretely. And then finally at the end I'll make some concluding remarks and discuss future directions and maybe relation to some other topics, kind of time dependent. So we start with 11D supergravity. I don't really know if I need to talk about this so much, but I will. So we have a metric, a 3-form, and a gravitino. F is dA. The bosonic action is Einstein-Hilbert, a kinetic term for F, and the Chern-Simons term. And we have the supersymmetry variation of the gravitino being this, where this is the Levi-Civita connection, and we have some flux term with some higher gamma matrices. Now, we want to restrict this to d dimensions. So, and the way we do this is we take a warped Minkowski metric ansatz, but we don't do what you usually do in this setup. Instead of taking everything to depend only on the external coordinates, we do the opposite. We take everything to depend only on the internal coordinates. And so we're effectively doing a reduction on the external Minkowski space. And then otherwise for the fields, we just keep things which are scalar with respect to the external space. So we can keep an internal metric, GMN, on our d-dimensional internal space. We can keep a warp factor on the external space. We can keep the internal components of the three-form gauge field and its field strength. If our dimension is greater than or equal to 7, we can keep the Hodge joule of the 4-form in 11 dimensions, which we call F tilde. And that can lead us to introduce a 6-form potential for that on the internal space, such that we say F tilde is dA tilde minus this being motivated by the 11D equations of motion, etc. And the A and the A tilde then have these gauge transformations which leave F tilde and F invariant as field strengths. So the bottom line is, the theory we want to describe has a metric, a 3-form, a 6-form, and a scalar. And it also has, if we consider the fermions, we have the internal gravitino, and we also have a spin half field. But I won't say too much about those in this talk. And then the action for this theory works out to be pretty much the same as the 11D supergravity action, except that we have an overall warp factor and a kinetic term for the warp factor as well. So that's the theory we want to recover from generalized geometry. Now, in order to discuss EDD cross R plus generalized geometry, first I want to discuss EDD cross R plus a bit in the language that we talk about it. So we consider a d-dimensional vector space F, and essentially what we do is we view EDD cross R plus under its GLD decomposition, where GLD is the natural action of GLD on F. So we construct these two spaces, which are called W1 and W2, out of F, and these turn out to be the decomposition of the fundamental and the adjoint of EDD cross R plus under this GLD. So in particular, we can write an action of all of these GLD terms on these GLD terms, or we can write a Lie bracket on these GLD terms, etc. And we can do all of the EDD cross R plus group theory we need in this language. So for example, a piece of this algebra we'll be immediately interested in is this 3-form and this 6-form of F. So I'll just show you what the action of those looks like explicitly. If we have a 3-form A and a 6-form A tilde, and we write V as V plus omega plus sigma plus tau, where these are just the GLD parts of W1, the fundamental, then we can write the action of A plus A tilde on V, the adjoint action, is given by this formula, where this means the interior internal product, and this is just some notation that we've defined, which is not particularly important, but it just deals with the strange index structure on tau, which is a 7-form times a 1-form. And this action, because it's nilpotent in some sense, you can evaluate its exponential exactly. It truncates at cubic order in the fields, and that gives you this. So the important thing here is it stabilizes the vector part of this generalized, well, what we will think of as a generalized vector, and it just adds these terms onto the remaining bits. So that's some EDD cross R plus group theory. So now we want to define this enlarged tangent space on our manifold. So what we do is we construct this bundle, which is much the same as W1 that I had on the previous section, except that instead of using just a vector space, we use the tangent bundle to the manifold. Now, in actual fact, E is not this. E is actually only isomorphic to this. And by that we mean it's twisted by gauge transformations. So it has a local representative in this bundle on various patches of M. And between patches, these sections are related by gauge transformations. Now, this is just the action that I had on the previous slide, except that we require our 3 form and our 6 form to be exact forms on the internal space. And
So,
yep.
exact? Why do they need to be exact?
Pretty much because these things are going to end up being the gauge transformations of the actual supergravity A and A tilde when we have them in the end.
Could they not just be closed?
Only on the overlap there, exactly.
Yeah, I guess it's only on the overlap there, exactly. But
I mean, that's sort of important if you want to have fluxes.
well, I guess because we're kind of assuming these patches are small, so we can take any closed form to be exact anyway.
Oh.
Yeah.
Sorry to do this. They're only on just 2 overlaps.
Yeah, so they're
But
just
you've
on
got
intersection of
if you
UI
have
and
3
UJ.
things-
And there's some co-cycle conditions for them as well.
I'm probably thinking that's stupid. Go on.
Okay. We can talk later if you still have. Yeah. So it's crucial that this gauge transformation is an EDD cross R plus elements, because that's what enables us to think of this as being an EDD cross R plus bundle in the end. Even though, in fact, the transition functions we've used to construct it are actually only these ones. We've only twisted it by gauge transformations, and we've kind of assumed diffeomorphism invariance from the outset. So really, the transition functions of this thing are only living in this geometric subgroup. But the fact that we have twisted it by the gauge transformations means that E contains the topological data of both the tangent bundle and the gauge fields when we introduce them. So this is quite nice. Now I'll just talk a little bit about notation for a minute. On one of these patches UI, we can introduce coordinates on that patch of the manifold. And then we can use the coordinates to construct a natural basis for E by just taking the natural basis of vectors and the natural basis of 2 forms, etc. And this, we write this as a coordinate index capital M, which runs from 1 to the dimension of E. And then we can write our local representative of a generalized vector as VMEM, where this VM capital M then runs over the vector components, the 2 form components, etc. And we can do the same thing with E star. E star is then going to be isomorphic to T star plus 2 vectors, etc. And we can write our partial derivative with a capital M index on it by just taking the ordinary derivative in the T star components and 0 otherwise. This is because we do not introduce any extra coordinates here. We're just talking about an ordinary manifold. But maybe I can comment very briefly that if we were to introduce extra coordinates and have a strong constraint, as Hadi was talking about in the previous talk, then we can basically choose a frame in such that this is true, so that locally what we're talking about here is the same. So with that said, we now want to define an analog of the Lie derivative in this generalized geometry. And this is the Dorfman derivative. So given a generalized vector field, we define this derivative. And it's written in an EDD cross R plus covariant form in such a way that it can act on any EDD cross R plus tensor. So the first term here is just the ordinary partial derivative along the vector. And due to our form of the partial derivative, this is literally just the partial derivative along the vector part of the generalized vector. The second term is written in a notation that we're going to use quite a lot, which means that you take your 2 objects and think of them as living in the tensor product space that contains both of them, and then you think of the projection of that tensor product space onto some irreducible part, which is indicated here. So here, we're thinking of having this being partial with a downstairs index and v with an upstairs index, and you project those two indices onto the adjoint representation of EDD cross R plus. Because that's then an element of the adjoint, you can quite clearly act on that with any ED. Well, you can act with that on any EDD cross R plus tensor. So, having written this, the first thing you have to worry about is it's defined using a local representative of the generalized vector. So you have to worry that it's well defined. And that means that you have to check that this is invariant under the diffeomorphisms and gauge transformations, which are the patchings of E. And it turns out that this is indeed gauge invariant and diffeomorphism invariant. So it's a well-defined derivative. The second interesting property of this is it has this Leibniz property. There's a paper by Baraglia where he discusses this and talks about Leibniz algebroids, and this is one of the properties he needs there. It's just a comment. And the reason we can think of this as being like the Lie derivative is because in the same way that the Lie derivative gives you the variation of a field along an infinitesimal diffeomorphism, this derivative gives you the variation of a field under an infinitesimal diffeomorphism and gauge transformation. You can see this most easily by writing it kind of like this. It turns out to be just the Lie derivative by the vector part of the generalized vector in the usual sense. And then the EDD cross R plus adjoint action of this gauge transformation, where this is omega is the 2-form part of the generalized vector and this sigma is the 5-form part. So the generalized vector is giving us a generator of bosonic symmetry, and this Lie derivative gives you the action of that. And finally, I'll just mention that we have this exceptional Courant bracket. Most people have discussed the Courant bracket before, and this is just the anti-symmetrization of this Dorfman derivative. So now we want to introduce generalized connections. And having introduced generalized connections, we'll use the Dorfman derivative we just wrote down to define torsion of them. So in order to define a generalized connection, you just do what you would always do to define a connection. You just take a joint valued one form. In here, we take E star. It's a section of E star which is valued in the adjoint, and you just write down the same definition as ever. Here, the capital A index is thought of as being a kind of a more general EDD cross R plus frame index. And then we can define the torsion by simply taking the difference between the Dorfman derivative with the partial derivative replaced with our generalized connection and the ordinary Dorfman derivative. And that gives you an action of a tensor on your EDD cross R plus tensor. And this tensor T is just a linear function of this omega here. And in principle, the torsion could depend on all of the components of omega because it's a linear function of it. So in principle, it could be a general section of E star times the adjoint of the group. But in fact, due to the form of the Dorfman derivative, we discover that the torsion always lies in a subspace of this. It always has a part that lies in E star, and it always has a part that lies in a representation that we've called K, where K is the representation which matches the embedding tensor from the embedding tensor formalism of gauge supergravities. So for example, in 7 dimensions for E7 is the 912 representation. So this is kind of interesting. And with that, we have pretty much all the structures that we need to do the rest. But I'm just going to take a couple of minutes to talk about another thing which is kind of interesting, although not necessary for the rest of the talk. And that is this other bundle which we've studied a bit recently, which we call N. N is a subbundle of the symmetric product of two E's, and its GLD decomposition is a 1 form, a 4 form, and some more complicated parts. And it corresponds to these representations of EDD cross R plus in these dimensions. And the interesting thing about this bundle is that it's basically the one such that you find that two partial derivatives projected onto this bundle vanishes. The reason for this is because our partial derivative, the way we defined it, only has components in its T star directions rather than the whole of E star. So we discover that this is indeed satisfied. So if one was doing the kind of double field theory approach to this construction, where one does have an enlarged manifold with more coordinates, one would suspect that this might be the section condition that you'd need to obtain to restrict to a smaller space of only d dimensions. And the d equals 4 case has been analyzed in depth by these Berman, Godauskas, and Perry, and they have indeed found that this is the case. But there are some other things we can say about it. One is that the symmetrized Dorfman derivative turns out to be in some sense an exact derivative of the projection to n of the two vectors that you're looking at. And one finds that if you look at the Jacobiator for the Courant bracket, you get a kind of a similar looking term to this, although it involves a Courant bracket as well. And furthermore, we have this potentially natural looking candidate to define a curvature in this generalized geometry, where you take the commutator of your derivatives and then you subtract off the derivative by the Courant bracket of them. The trouble with this is that it doesn't give a tensor in general. But we discover that if you restrict V and V prime to live in a subspace of E such that the projection of them to n vanishes, then this magically does become linear in V and V prime. So it's kind of clear that there's something interesting going on here. There's more to say, because the projections to n are measuring the failure of all of these things: the antisymmetry of the Dorfman derivative, the Jacobiator of the Courant bracket, the linearity of the curvature. So this is just an interesting observation.
So that curvature operator you defined there, projected down,
yeah.
Does that give you the sort of curvatures that we've been looking at? I mean, in the sense,
not really.
Give something different.
Yeah, the curvatures I'll talk about later on. I don't know exactly what the connection between them and this is. I think that's the correct statement at the moment.
When you say tensor, I mean, you mean tensor under generalized Lie derivatives, or tensor under ordinary tensor?
I mean tensor under EDD cross R plus changes of frame in this bundle. Yeah. Okay, so back to the main point of the talk. So in the next section, I'll talk about the generalized metric, and this reduces the structure group of E to this subgroup HD. So first I'd better say what that is. And it's the usual maximal compact subgroup of EDD. In fact, because we're going to want to consider spinors, we're always going to take the double cover, which is we call HD tilde, and that's given by this. And a representation that's going to be important for the discussion is this one that I've called H-perp, which is such that H-perp plus the adjoint of H is equal to the adjoint of EDD cross R plus as a HD representation. Now, it's well known that these supergravity fields parameterize this coset. And so what we can do is, on a patch UI of M, we can build a generalized metric, capital G, from these fields. Now, the idea being that we want to take a kind of a inner product of two generalized vectors using this G, which is a scalar. And we have to bear in mind that these gauge fields are only defined on this patch, and they have a patching rule, which is this. And it turns out that the patching of the generalized tangent space exactly counterbalances this patching in such a way that this G of V and V prime is a well-defined scalar. Now, I'm not actually going to give an expression for the generalized metric, because what we're actually going to do is we're going to move to a kind of a Vielbein frame for it, to make so that the expression for the generalized metric becomes simple. So we can construct such a frame by taking an ordinary Vielbein for the ordinary metric G and its dual basis for all the forms. And we build this conformal split frame, which is essentially the EDD cross-action of the 3 form and the 6 form on the first part of each of these expressions, and also a rescaling by e to the delta. And in this frame, we can see that the generalized metric is very simple. If one writes out a generalized vector in components like this, one can use these components to build a vector and a 2 form, etc., like so. And one discovers that these things are patch independent. They don't depend on which patch of the manifold you started from. This is because, again, the transformation of the gauge field exactly counterbalances the patching of E. So we finally made our isomorphism between E and the vectors, 2 forms, etc. Now, in this frame, we simply just write the generalized metric as the square of this vector and this 2 form, etc., using the ordinary metric. And there's an HD family of frames which satisfy this, but the conformal split frame is actually only a special kind of them. It's not a general one, but it's one that's convenient for doing calculations. Now, the HD structure actually also gives us a volume form, which is related to the determinant of the generalized metric. In the coordinate frame, we can evaluate this as such. It's this determinant of the ordinary metric with some warp factor. And we'll need this later in order to be able to write integrals of things. So the next stage is we want to construct the analog of the Levi-Civita connection in this geometry. And so first we have to make it HD compatible, and that just means that it annihilates the generalized metric. Secondly, we need to make it torsion-free, and we can build a generalized connection from the ordinary Levi-Civita connection for the metric GMN as such. Here, this term simply just means the action of ordinary Levi-Civita on the vector and 2 form that I had on the previous slide. And we add this extra tensor sigma, and then basically just see what constraints we need sigma to satisfy in order for it to be torsion-free and compatible. And we discover that there actually always exists a family of such sigma such that D is torsion-free and compatible. So there's no unique solution here. However, the torsion-free condition does fix some of the components of sigma to be the supergravity fields f, f tilde, and the derivative of the warp factor. And we can write very explicit expressions for this. If we decompose everything under SOD, the HD algebra looks like 2 forms, 3 forms, and 6 forms. And so we can write like a vector contracted with the sigma, which is an element of the adjoint of HD, as these 2 forms, 3 form, and 6 form parts, and the expression is this. where this C represents the parts which are not fixed by the torsion conditions. So, for the most of the
Where did you choose the vector and the two form and discard the 5 form?
Sorry?
For the torsion-free condition, if I noticed correctly, you said you applied it only to the vector and the two form.
Oh, and all the other bits as well. Yeah.
Is C constrained at all?
Yes, C is always constrained to live in a particular HD representation, but it's kind of a bit awkward to write it out in this language, so that's why I've just called it C here. And these parts precisely correspond to the other irreducible parts of the connection under HD. So, for the rest of the talk, I'm going to talk about spinors quite a lot. So I'll just briefly mention that again that we're taking the double cover of HD, which is HD tilde, so that we can discuss this. And that the spinor of spin D very naturally is promoted to this representation S, which is the fundamental representation of HD tilde. And the gravitino field also can naturally be seen as another representation, which we call J of HD tilde. And if it's quite easy to embed the previous slide that I had in the Clifford algebra, so we can act on a spinor, you just embed it as gamma 2, gamma 3, and gamma 6, and contract with the 2 form, 3 form, 6 form of gamma matrices, and then the action becomes this for the torsion-free compatible connection. So we kind of have this issue that the torsion-free compatible connection is not unique. But it turns out that we can just...
Excuse me.
Yep.
It's not obvious to me that this will make an algebra. But it's not, why will this set of 2, 3, and 6 make an algebra?
It's because it's the algebra that preserves the C intertwiner for the Clifford algebra in all dimensions.
For example, in 11 dimensions, it's 1, 2, 5.
That's because in 11 dimensions you don't have the C intertwiner, you only have the other one. You have the minus transpose intertwiner, whereas in these cases I think, or actually no, that's not quite true. This gamma 2, gamma 3, and gamma 6 just always turns out to be the things that preserve one of the intertwiners of the Clifford algebra. So in 7 dimensions it's the Hermitian conjugate intertwiner. In 6 dimensions, it's the transpose intertwiner, etc. It does always form an algebra. In these dimensions, I suspect the complaint about 11 dimensions is because the dimension is too high. We're only thinking about dimension less than 7 here. Yeah. So, where was it? So if we hit elements of S and J with these torsion-free derivatives, we discover that we can make certain projections of them which are uniquely defined operators, such that all the undetermined bits of the connection drop out. And I kind of couldn't resist putting in a little comment about fermions, which is that in our supergravity, we have our fermions, the gravitino and the spin half field, and we can promote these to these HD objects. And we discover that the equations of motion for these fields are quite simply just the operators that I wrote on the previous slide. And also that their supersymmetry variations are also just the operators that I wrote on the previous slide. And from this, we can become inspired to...
Can you go to your previous slide then? Sorry.
Yep.
So that was so those operators were there for torsion-free compatibility.
No, these are just derivatives of objects that you can write down, and you were assuming here that the derivative D is torsion-free and compatible.
Yeah. Okay.
So we know by the closure of the supersymmetry algebra that if we quite simply substitute this into here, that has to give us the bosonic equations of motion. So that's what we do. We just
So small index J and F, and this product, they refer to some projection you said, yeah?
So J and S refer to these HD representations. S is basically just the spinner, and J is the representation that the gravitino lives in. This is again this notation where you have two objects and you project the tensor product of them onto an irreducible part of it. This should all become clear in a couple of slides' time when I write some explicit expression. So again, we just substitute the supersymmetry variations into the fermion equations of motion, and we know that this is pretty much guaranteed to give us some tensors R0 and R by this closure of the supersymmetry algebra, such that these things are basically the bosonic equations of motion. And it turns out that that's exactly how it works. You can combine these into thinking of them as being the scalar and non-scalar parts of some Ricci tensor, which lives in the representation H perp, which is basically the tangent to the coset, so it has the right number of degrees of freedom. And this then does indeed give the bosonic equations of motion. The vanishing of this Ricci tensor is the bosonic equations of motion. A very brief comment is that you can also write the same operators in this form, where we have anti-symmetrized derivatives and projections of derivatives to n star. And this is going to reassure us that the second derivative parts of epsilon on this left-hand side are going to vanish because these were precisely the projections of the partial derivative which vanished. So now I'll just whisk through some SU8 expressions.
I was going to say, it's entirely my fault, but you have to finish in 5 minutes.
Okay,
Which is a little bit early.
That's fine, yeah. Under SU8, the 56 decomposes appropriately so that you get this index structure. The spinner becomes 8 plus 8 bar, the gravitino becomes 56 plus 56 bar, which is 3 antisymmetric indices, and we can write the generalized metric like this, and other expressions. But the point is that my unique operators, you can see how to construct them here. So for example, for this one, you're looking at antisymmetric alpha beta hitting this epsilon gamma, and if you take the projection which corresponds to just antisymmetrizing on all 3 indices, that gives us some projection, and that turns out to be unique for the operator D. And using similar things, we can write down the supersymmetry variations of the fermions and the fermion equations of motion, and also the curvature, just by substituting in as before. Where here we have this antisymmetric thing on 4 indices, which lives in the correct representation. It has some complex soft-duality condition. And the scalar curvature evaluates to be this, which is just the warp factor equation of motion. And if you integrate this with our volume form that we had before, that gives you the action. So that's kind of the main body of the talk. I guess maybe I'll skip these things for lack of time. I was just going to say briefly that the same construction describes type 2 theories with RR flux if you take GLD-1 decompositions instead. And a really good application for this is supersymmetric backgrounds. It turns out that this SUSY projections can be seen to be equivalent to the vanishing of the connection on the spinner, so the supersymmetry conditions end up just being special holonomy for the generalized connection, and the holonomy is the stabilizer of your killing spinners, so that for n equals 1 you land up with just an SU7 structure on the 7D internal space. For n equals 2 it's an SU6 structure. And there's a way to see the relation to the embedding tensor formalism in the case where you have a maximal number of supersymmetries here. So I'll conclude quickly. So we've seen that EDV cross R plus generalized geometry has given us a very nice geometrical description of our internal supergravity theory, in which the bosonic sector has just become Einstein gravity for this generalized geometry. And I haven't shown all of them, but you can, in this formalism, write all of the equations with your local HD tilde symmetry a la DeWitt and Nicolai. Although, again, only considering the internal sector, they did the entire theory. So I shouldn't claim too much. And our future directions are, well, there's a question about what happens for d greater than 8. It looks like you have to understand the dual graviton to do that. So there's kind of unclear what to do there. We didn't really put in supersymmetry, it came out kind of by magic, so you can wonder, you know, can I extend HD to a supergroup to make it even, you know, include even more stuff geometrically? There's implications for the structure of higher derivative corrections, I gather that lots of people are thinking about that. And mathematically speaking, this is an interesting new kind of algebroid, and so there might be interesting statements to make there. So I'd better stop. Right. Thank you. Thanks for your attention.
There's now a discussion session in the discussion room, and so I think we'll adjourn there immediately, and you can take questions there.
Okay.
There's a group of people who are interested in Alan Turing and computer science who are about to invade the lecture theatre, and it's best not to anger the computer scientists. So we'll be moving into discussion session, and we can take questions then first.